the real world changed and what that means for our education as we go forward. We have a huge number of machines which are ever increasing in their abilities. And we have education that goes back to ancient Athenian times in many respects in every country. And the question is, how do we match these two together? And that's really what I want to spend most of the talk addressing. Well, I thought I'd start by explaining what I do during the day and then go on to this topic. So what we really do is to try and build the best technology for computing results. So we want to use computers to do as much as we can in the world to simulate things, to try to model things, to try and get better answers for questions that we have in the world. And that's kind of the central role that we see ourselves doing. Push the boundaries of computation. Push the envelope of computation into all areas, everywhere where computation can help you get decisions, get answers, try and optimize that at all levels. And in a sense, my day job is to try and take over ever more human tasks. We want the computer to be able to figure out and help you work out more and more things in life that you might want to do or that we want to do for society. And one of the ways we do this is to try and build a whole system that can try and allow you to construct ways to automate math for everyone. So this is an example. I'm running in a new piece of software, and you can see that it's correctly identified me as a person from the video feed. And if I hold up, for example, a pen, it may or may not get that exactly right. It thinks it's a matchstick, or it thinks it's a pencil. That's a little bit closer. And you might also get it to, for example, check what my gender is, and hopefully to figure out I was male. And it may be kind or unkind in terms of deciding my age. That's very unkind. I'm younger than that. So you can see that these things don't always work perfectly, but the idea is to achieve as good a thing as possible. So if I say happiness, I could even hopefully try and tweet that. And with any luck, our technology stack has managed, in fact, to tweet that to my Twitter stream. So one of the things we're trying to do in my day job is to try and make computers do as much as possible, build the ultimate technology stack to allow computation to be applied everywhere. So that's the day job, computation for everyone and smart automation to achieve that. So what I want to spend most of this talk talking about is my evening job, and that is the other way around. What do we do to fix up the human in order to make them work with the computer? And you may think this is paradoxical or contradictory. If I've spent all my day trying to make the computer cleverer, why am I now saying that maybe we need to do something with the human? Well, the thing is, as you make the computer cleverer, you want the human to step up to new ways to interact. You don't want the human just doing the same as the computer now does. And so that's what I want to talk about. I want to talk about computational thinking and how that relates to what the human job now is that we have artificial intelligence. So let's start by understanding in some more detail, how is it we have what I would call ubiquitous computation. So what do I mean by that? You know, we all carry around phones, we have computers available, we have huge computing power available to us virtually all the time. And so I call that ubiquitous computation. Now what has that done to change the real world of STEM, of science, technology, engineering, and maths? What does that really do? How do we change things there? Well, one of the ways this changes is that maths or computation is now applied in almost every walk of life. So in the past, maths was applied to things like architecture, it was applied in accountancy, it was applied in physics. An early success was figuring out how the planets went around the sun. But it wasn't really applied in places like prototyping complex models or linguistically interpreting humans, or medical imaging, trying to interpret images we have of people, or in trading, finance, or in archaeology. Nowadays it's commonplace to use mathematics for image processing in archaeology, not a domain you would have expected it in, or in biology. And these are all very new areas of the last few decades that mathematics has been applied to, and they're only possible because we have mechanized computing. You cannot do these if you do not have a computer that does your calculations for you. But here's a simple sort of demo. So what I'm going to do here is I'm going to ask our software here to look up in the human genome any place where that sequence appears. And it turns out, live, in a few seconds, I've pulled up everywhere in the human genome which chromosomes that sequence appears on. And so it's automatically done a search through all of the chromosomes in the human genome and figured out the matches to that sequence. Now you just have to understand how amazing this is. I'm on a laptop computer that's thinner than most books. And yet in about 10 or 15 seconds I've pulled up this sequence that people thought they couldn't even sequence the human genome a couple of decades ago. And now instantly I can pull this up. So that's the kind of transformation we see from ubiquitous computation. And you can see there were quite a few setups of this. Now, of course, data we have coming in from everywhere. So the amount of data that we see in the world is going to increase massively. And so one of the main areas that computation is now applied to is how to deal with this data. Are we getting the best answers we could be getting out of such data? And one of the challenges which I want to talk about is how we set up, so to speak, citizen data analysts. You see, one of the challenges of living in the modern world is you have to know something about data. All the time your governments, your other people are throwing data at you. And you need to understand how to work with that data and not be fooled by it. So we have many challenges in society to know how to handle this extent of ubiquitous computation. Now, one way I like to think about this is both ends of the spectrum of what humans should be involved with. I said it's very important to think of how you evolve what the human needs to do with respect to this computation. And one basic question is, what are the modern survival skills in the world? You know, many, many years ago, it was important to be able to light a fire, for example, because you needed to avoid wild animals coming to eat you. In most places now, that's not your main survival skill. I'm still here, and not very good at lighting fires. So what are the modern survival skills? Well, there are many survival skills to do with data and understanding computation that are really quite critical just to live in a society. And so we need to think hard about what those survival skills really need to be in a modern education setting. But the other end of the spectrum is, what are the value-added skills that humans bring when computers are there? I mean, what you don't want to do is just educate people so that they can pretend to be computers. The question is, given that computers do ever more intellectual, intelligent things with artificial intelligence, what is it that the human ought to be doing? What is this top value-added type of thing? And so I'm going to argue that there is a core human skill that everyone needs to learn some of. Some people need to learn a lot of it and become expert. And I'm going to call it computational thinking. A way to understand how to run the process of computation with modern technology of computers and really make progress in answering questions that come up. Both progress just to survive in an everyday way, and also progress to really add value to what the computer can do. Now, the big question I have, if you look in schools around the world, high schools, where would you expect computational thinking to be taught? And the answer is very clearly mathematics. Mathematics is the centerpiece of our computational education today around the world. It takes up a lot of time in curricula. And the question I want to ask is modern computational thinking actually being manifested in maths education today around the world? And I have pretty bad news, and the answer is I don't believe it is. In fact, I think mathematics is probably about 80% the wrong subject in schools. It's a rather shocking number. So around the world, we have perhaps people learning mathematics for a minimum of 10 years of their life, many hours per week. And it's probably the case that 80% of that time could perhaps be better spent for a modern computational era. And let me explain a bit more why I say that. The key thing to understand is that in the real world, outside education, when you use mathematics or computation, computers are calculating the answers something like 80% of the time. Computers do the calculating in the real world. By contrast, in education, humans do almost all the calculating. So when you're studying for mathematics, the human does, let's say, 80% of the calculating, and sometimes you're allowed to use a calculator or a computer to add to that. So these are basically completely different subjects, and they become more different over time as the computer is able to do more and more things. So on the one hand, you have humans doing 80% of the calculating in schools, and on the other hand, you have computers doing 80% of the calculating in real life, and the two do not match. And that's the central problem with today's maths education. Well, let's zoom out a little bit and ask a question. Why exactly does everyone learn maths? Right? Virtually every country in the world thinks that you should learn maths, as I said, for 10 years of your life. Why is this? I mean, there are very few subjects that people think you should learn like that. I mean, history is a subject that's common in virtually every country. Your own language is a subject that people think you should learn. But there are many subjects people think you should only learn for a year or two, or maybe it's optional. Music, for example. So why is maths in this category? And are there good reasons why it should be? Well, I think there are three good reasons. First reason is because it has been the major empowerment of economic growth and technical jobs for the last maybe 4 or 5 decades at least. Mathematics has really pushed the top end of the value-added jobs, and modern mathematics can do that more. The second reason is for what I would call everyday living. Just to survive, as I mentioned, those basic skills, you need some basis of maths. And the third reason is what you might call logical mind training. Being able to think about problems, even if you're not actually using mathematics for those problems explicitly. Being able to think and reason. Can you look through what people are saying and understand that and believe that you can have some logic to that thought? And of course there's a very ancient tradition of logical thought, and of course that's ancient Greece introduced much different types of logical thought, and in a sense we now have computational thinking is one major strand of that sort of thinking, and being able to do that is important, both for everything from your livelihood to democracy, which also nowadays depend on things like understanding data, not to be fooled. And one of the things we have to understand, as I said, is whether everyone should learn this subject. And you need to ask questions. Is it reasonable for everyone in the world to learn ancient Greek, for example? Now, in Greece, I think you do learn some ancient Greek, though there has been some discussion at the moment about whether you really ought to be learning ancient Greek or not. And I'm sure there's good value. And I enjoyed in England, in fact, learning ancient Greek. And it's great for people to try many different subjects to see what they individually find interesting. But you then have to ask, should everyone around the world learn ancient Greek for 10 years of their life? And I think the answer is it's hard to justify that. Well, I would argue the same for today's mathematics. But I think there is a mathematics that is very well worth learning, and that's this computational mathematics. So let me explain a little bit about the difference I see between mathematics today in education and the mathematics I think we need. So here's the problem. What is mathematics? What's the process by which you do mathematics? or learn mathematics. And I think mathematics is a four-step problem-solving process. And the steps are roughly this. You start by defining a question. So for example, if I say, a typical question might be, if we seal this room and turn off the ventilation, and I talk for much too long, how long could we survive in this room for? That might be a question you might want a computational answer to.
Eternity calls you.
Say that again?
Eternity calls you.
Eternity calls me. Well, hopefully not. So, the next step you might do is to translate that question. The great power of computation is you translate that to an abstract form. So you could discuss this in English or in Greek, but it won't get you as precise an answer, probably, as if you translate it to abstract mathematics. Why is that? Because mathematics, by abstracting ideas into a common way of representing them, many different types of observations into that common structure, you can use hundreds of years of being able to compute answers from that abstract start. And so this magic step of 3, where you compute the answer from the question, you start with an abstract question, and you then compute an answer. And this is the sort of magic that mathematics achieves. And then you get a result, x equals 3, and you then say, can I interpret that? Maybe it's 3 hours, and probably rather longer than that, actually. And you see whether that result seems rational for the question that you asked. So this is the process that you are going through when you use mathematics or when you do computation. And the problem in education right now is we're spending almost all our time trying to do step 3 by hand. So we're doing virtually none of these other steps. Our students are not really learning how to define the question or translate or interpret the results. They're just learning how to calculate things by hand. But what we ought to be doing is using the computers primarily for calculating, for step 3, and using the humans to do much more of step 1, 2, and 4, with harder problems, more realistic problems. That's the central issue that we need to address. And as I say, maths is a problem-solving process. So you define the question, you translate, you compute, you interpret, and you sometimes do this many times until you reach success, hopefully at the end of it, and get an answer that you think is really good for what you want. Now, one of the things that comes up is, in schools, you often do very simple problems because they're the only problems that you can calculate. So this is a problem that most people probably solve at school, although they do it by hand. But you see, when you have a computer, you may have the same concepts, the concept of using an equation, in this case, or simultaneous equations, but you could just make them calculating a bit harder. So in that case, I've calculated it by making the cubic equation. And here's the really sad thing. What I did there is something that most students, after 10 years of learning mathematics at school, cannot do. And yet I did it in a few seconds on my computer. And it actually gets even worse than that, because if I talk to my phone, solve x cubed plus 2 equals 2y, and y minus x equals 5. If my phone is happy, okay, so it's got many answers, but if I just show you on the screen, you can see roughly there. Our Wolfram alpha here has generated this answer in a few seconds. So just to summarize what I'm saying there, I have talked to my phone, and in maybe 10 seconds, I've got an answer from my phone that most students, after studying mathematics for 10 years of their lives, cannot produce. So you've got to ask, why are we teaching them that? That doesn't seem to make a lot of sense. What we should be teaching them is how to do higher level problems, not pretend to be a computer. Because we'll lose. If humans pretend to be computers, we'll lose that race. Humans are not as good at computing as computers. But we can be much better at higher level problem solving, at least than today's computers, and then we need to go to the next step. So here's another problem with today's curricula. They're very centered on the mechanics inside. So these are examples of the sorts of things that you probably have when you learn mathematics. You know, similar triangles, inverting matrices, the chain rule, solving simultaneous equations like I just did. But actually, really we should have mathematics that's centered on problems that you want to solve. You know, a problem that every 7-year-old has. What's the perfect password for my login? I don't want my friends to break into my computer or to my phone. What should I set as my password so they don't break into it? It's a standard thing. A problem that teenagers have. Am I normal? What does normal mean? Is there a mathematical way to think about normal? Is it my height, or is it my shoe length, or is it something else? How do I design controls for a game? Am I cheating? Can you tell whether somebody else is cheating? And there are also other questions that may seem more esoteric. What's a beautiful shape? Well, you know, it's clear that the architects of the Parthenon thought about this problem. Whether you think they explicitly thought about the golden ratio or not, and the golden spiral, that's open to question. But there clearly was some mathematical intuition about what was a beautiful shape versus what wasn't. So there are many of these much fuzzier questions in real life that you want to use mathematics for, and you can only do that for many of these when you really use modern computation, and that's what makes using it so exciting. The thing most governments misunderstand about mathematics education, if you remove the computer from mathematics education, you will remove almost all the context. So what do I mean by that? You know, mathematicians often don't like me saying this, but before modern computing, mathematics was only used for a small number of things. And it was very successful for those. It was very successful, as I said, for bits of physics and accounting. But it wasn't successful in many areas of life that we see it in today. And the only reason that those areas of life now use mathematics is because computers mechanize calculating. If you remove that mechanization from education, you will remove the context. So there are no real biology, computational biology questions without a computer that you can actually do. You can't do data science. You can't do image processing. Those are modern uses of mathematics when you have mechanized computing. And so one problem that occurs in education is people try and make pretend word problems that try and simulate what you'd actually do in real life, but they're not really they're rather fake. And the students and the teachers and everybody understand these are not real problems. And so then a lot of the students switch off. And they think these are not very interesting things. If you have a computer, you can do much more real problems. Another problem if you remove the computer is you end up with a different tool set. You know, it's like if you're doing DIY, fixing your house, right? If you tell people you are not allowed anything with a motor, you're only allowed to use a screwdriver and a hammer. Those are the only tools you're allowed. You're not allowed to use an electric drill or an electric screwdriver or a measurer or anything. It means that people get a very different set of experiences as to what they can achieve. And they don't necessarily apply the right tools for the job. One of the problems is in the modern world, not so much that the tools are not available. We all have computers available much of the time. The problem is, which tool do you use for the job? It's a very hard intellectual problem. Do I use machine learning? Do I use algorithmic approach? Do I use numerics? Do I use symbolics? Do I use pattern matching? What is the approach I use? And you need to gain experience. Students need to gain experience of the different tools and when they apply in different problems. And another way to think about this, if you're an economist, is to think about the cost-benefit analysis. And if you think about the 4 steps I explained, step 3 when you do computation used to be very expensive. You had to have humans doing all of step 3. So we focused all our energy on doing step 3 by hand and learning it. Now step 3 is very cheap. Computers are very powerful and they do lots of computation. It's very cheap to do step 3. So we need to focus our energies on how we set up the problems and how we define them and interpret them. So it's important to think about where the tool sets are that we need. So here's a typical example we tried in a classroom. Can I spot a cheat? And so in this example, what we did is we gave half the students a coin to toss in reality and note down whether it was heads or tails. And we gave the other half of the students, we told them to type this directly into the computer and just cheat, like I'm doing now. Not actually do the experiment, but just try and cheat like this. The question is, can the computer tell, if you type in the real results and you type in the fake results, can you tell who's cheated? And the answer usually is yes. So in this example, I got the computer to analyze what I typed in, and I only passed one of the 5 tests. You see, we did a bit of data science on what I typed in, and by being a bit smart with the data science, we figured out that probably I was cheating. So the students are amazed by this. They said, how did my teacher know that I cheated? And the answer is data science. And so we then get the students to try and analyze ways that they might think about how you would, what was different about the results that they typed in and what was different about the real experiment. By the way, I'm just going to cheat. I'm going to do a different sort of cheating. I'm going to get the computer to pretend I actually tossed the coin by generating random numbers. So it's a sort of semi-cheat. And I'm going to do this, let's say 200 times. I'm going to paste in the results. Whoops, what have I done here? I think I want to do, that's why the thing I want to do, integer, I've typed in the wrong number. Let me do this later, I think. I've typed in the wrong expression. It's late in the evening and I can't remember what the right thing is to do here, but oh, I know what I want. I want random integer. Here we go. That's what I was looking for. So let me do this 200 times, and so then I didn't get heads and tails. I got a list of zeros and ones, but I think the thing should be able to interpret this as heads and tails. So let me copy that and let me paste that in as data. And so this is what the computer is generating. You'll see, because it has a good random number generator, it's in fact passed, in this case, all of the tests. So I sort of semi-cheat. I pretended I'd done the experiment, but I was a bit more sophisticated about it. So this is all to do with patterns in data and the fact that when you type them in yourself, you overcorrect, and you tend to type too many, too even, and it doesn't pass the test. So this is a little bit like how banks detect credit card fraud. It's the beginning of the data science you do for that. And so you see this is a real problem. You can do it with a computer. It's a real messy problem, the kind of thing that you really use mathematics for in the real world. So one of the things we've been doing is to try and build these into an approach to be able to learn mathematics from problems. And this is I thought I would show you a simple example of our computer-based maths project. And this is like an electronic book where you are learning different things about modeling and how things work in different ways. And a typical example in here is you have a model. And here's a model. This particular module is about how fast could I cycle round a cycle race, like the Tour de France in France, that is a common cycle race. And this is a model for cycling and how much power you need as a cyclist. And you see, one of the things we want students to be able to do is to assess models and see whether they think that they make sense. But then later on in this module, we get them to program modules, to simulate them themselves, and to use their own image processing to work out whether how they will do if they're cycling, whether you lean over more, you have less wind resistance, and so forth. So we want to actually have real messy problems with the real tough equations of air resistance and fluid dynamics. But you can do all of that if you allow the computer to do the calculating. Now, I wanted to just make very clear in what I'm talking about two major effects of artificial intelligence. And people in education sometimes confuse two different uses of the computer in the classroom. And I wanted to be very clear about what these different uses are. So what I've been talking about all the way through this is changing the subject that you need to learn. Because, as I explained, the subject is different because computers are used in the outside world in order to do that subject, and they've made a massive difference to the subject of computation and maths. But there is another way that computers can help, and that is in how you learn whichever subject you're learning. Computers can potentially act as the teacher or help the teacher to teach you in different ways, the pedagogical approach. And that could be true in history, or in mathematics, or in science, or even in ancient Greek. But when you often talk to people in education, they think that the two are the same thing, and they are not. They're very different. So AI really has two things it's doing. It's driving the need for change, because it's changed the real world fundamentally, and it's also providing the tools to allow you to pedagogically approach that new world, or indeed even old subjects in a different way. But just to stick on pedagogy for a moment, there are ways that it really can help, and we shouldn't forget this. I think you can make learning much more personalized. So at the moment we have typically teachers teaching classes, and we have lots of people in the class, and they have to do more or less the same thing. There are opportunities in the future to be able to have the teacher focus more on individual work, while the computer does more general instruction, and for the computer to personalize what it delivers. Assessments can also be more helpful. The content can be much richer. Our Wolfram Alpha allows you to pull in real data as you're doing a problem. So that means you can actually think about today's problem rather than data from the past. And being able to adapt to the student. And also going off on a subject you're specifically interested in as opposed to just everybody else's subject. So there are many effects that AI can bring to pedagogy, as well as the fundamental change I want to see in the subject. So just to be clear though, AI on subjects changes what humans need to learn. And as I tried to explain, it changes what's for the computer and what's for the human. And whenever you think about this, it's good to look in the real world and to see how the computer changed, and then bring that back into education. Now, one thing I'm often asked is, how does computational thinking, maths and coding fit together? Many countries want to teach coding, and I know there's an effort to start to think about that in Greece as well. The way I think about this is computational thinking is, in a sense, a way that you learn how to do STEM and life. It's a way of thinking. Maths, in a sense, is a specific area of domain knowledge, which computational thinking, and it's very interlinked with computational thinking. But there are areas that you would think of as very mathematical areas, and there are other areas of computational thinking you'd think were a bit outside that. Coding is a way that you write down and express computational thinking, or maths. So if you remember my 4 steps: define, abstract, compute, and interpret. You see, step 2, when you take the real problem, how much air do we have in the room, and you write it down, how do you write it down? You see, in traditional mathematics, you'd write it down with very nice, very fine letters, some of them Greek, and you'd express it that way. In the modern world, you write it as code, because you want the computer to do the calculation, but also because traditional mathematical notation is in fact ambiguous. And so you need to write it down in a way that can be clear for everybody, including humans. So in the end, coding is really several things. Coding is a way in which you write down how the computation is to be done. In a sense, you abstract what the input for that is, and you write down, in a sense, you transfer the idea from you, the human, to the computer. So it's very important that people have a way to express this. But in my view, it should be part of the same subject. There should be one subject at school that's computational thinking that includes mathematics and coding together. And I thought I would try and write a piece of code for you live while I'm giving the talk. So I thought that I'd been talking for sufficiently long now that you might have got very bored of seeing my face. So I thought what I would do is I would try and write some code to block out my face. And so I'm going to try and do this as I'm talking. And so what I'm going to do is I'm going to show me, the dynamic image of me, and I'm going to try and do that, and I want to apply to that a rectangle on top of me, and I want to do it on top of my face. So I wanted to find my face, and I wanted to then put in the rectangle on top of me, and hopefully, there we go, I have now successfully blocked out my face, so at least for a few seconds you do not have to look at me, at least on the screen. So it's very interesting. This is my way of expressing what idea I had about computation that I wanted to do. And you can see that I've managed to do that in a very small amount of code, and I've managed to do it live while we're actually looking at this, this notebook that I have here. Now, by the way, that's an example of our Wolfram language that was mentioned in the introduction kindly. And the idea in the sense of Wolfram language is to make a very succinct code that, in a sense, allows you to express things very, very quickly, and assuming this sort of algorithms are built in. And now, of course, code in a traditional way is slightly different from another thing we do, which is linguistics. And a typical thing you might do with linguistics is to ask something like, let's say, sheep in Greece versus, let's say, people or population, let's say, of London. And you see, this is a sort of sloppy query where you might try and understand the difference. And in fact, it's quite closely matched. You can see that the population of sheep in Greece is reasonably closely aligned with the population of people in London, which is perhaps telling one something about the population of London, maybe, or maybe not. But it's interesting, you see, the connection between sort of linguistics in this sort of sense and computer language. Computer language is much more specific, but you also still want these sort of linguistics to operate so that you can quickly talk to things. And one of the things we've been trying to do is build this complete technology stack to enable that. So in a sense, our strategy has been to build this ultimate stack that goes from utterances of words to interactive things to the language that I showed you. Well, I want to spend a few minutes to talk about what people object to what I'm saying. So often when I give talks like this, and maybe we'll have some questions afterwards, people say, "You're wrong. I don't agree with you." And I thought I would say some of the things they say to me and explain why I disagree with that, and then we can have some different questions afterwards. One of the objections people say is you've got to learn the basics first. You don't really want to learn and by which I think they mean you should learn to do mathematics on paper before you learn to do it on a computer. So I asked them back, basics of what exactly? If you learn to drive a car, are the basics of learning to drive a car learning how to make an engine? Well, 150 years ago, or I guess it's nearly 120 years ago, it probably was. The person who drove the car was also the person who built the car. But you see, we're a long way from that. When you drive a car now, there's lots of automation in between. To learn how to drive a car is a very different skill to learn how to make a car. And the same is true in mathematics. The people who make new frontiers of mathematics, there are a small number of those people, they're very important, but most of the population does not need to learn the making of the mathematics. They need to learn how to use it in the best way possible. And that's still a hard task. The other thing people sometimes do is they confuse the order of invention of the mathematics with the order in which you should learn it. And something I love to tell, I have a daughter called Sophia, a Greek name, and when my daughter was very young, maybe 4, she used to enjoy making paper laptops. And I discovered that paper laptops were things where you took a piece of paper and you folded it in half, and you drew a screen on the top, and you drew keys on the bottom half, and then you folded it, and you'd unfold it. And one day I said to her, you know, when I was your age, I didn't make paper laptops. Why do you think that was? And she thought very carefully for a few seconds, and she said, no paper. To somebody who's learning a subject, it doesn't matter what the order of invention was. It doesn't matter that paper was invented before laptops. What matters is what the best tool is for the job, and it's very important we get that best tool for the job. So to my mind, what are the basics? I do think you have to learn basics mathematics, but I think the basics are those 4 steps. Really knowing how to apply those 4 steps of computation with a computer to hard problems, and getting good experience at being able to do that in many, many different areas of life. So here's another thing I sometimes hear. Computers dumb maths down. This one really annoys me, actually. So people suggest that if you're using a computer, somehow you have to do less thinking. Well, of course, any tool, including computers, can be applied badly. If you have bad curricula that try to use computers to do the wrong thing, of course this can occur. But if you want to use computers correctly, I ask a very simple question. Do you think that science, technology, engineering, maths, STEM subjects in the outside world have become less conceptual since computers existed? And the answer is overwhelmingly no. Life is much more complicated in the outside world because we can do all these computations, so we go much further. We want to optimize things. We build our smartphones. We try and control things. We do many, many more things than we did in the past. So life in the outside world is far more conceptual, and one of the key reasons for that is we have mechanized computing. So why would you think that computers in education should dumb it down? It's a crazy idea that because you have computers, you can somehow make everything easy. Computers mean that you can attack much harder problems. And so I think this is really wrong, unless, of course, you don't use them the right way. You think they're all for pedagogy and not for changing the subject. And one of the other things that I point out in some of these objections, there are many other things people level at me, but people are not very motivated in most places to do mathematics today. Many students are upset. They're told they have to do this mathematics. They don't really understand why they do it. Many of them find it very difficult. Teachers find it hard to teach often. And in the end, most of the students don't learn most of mathematics. One way you fix motivation is to attach the subject to that student's life. You know, if I'm doing something that seems to apply to my life, age 10 or age 12 or age 6 or age 18, most people are more engaged in that than they are in something that they see no connection with. A few people really like the abstraction first. So one thing I like to say is abstraction is a very important idea, but use abstraction to help you solve problems. That's what mathematics should be doing. Don't use abstraction to scare students off trying to solve problems. At the moment we use abstraction in the classroom, we say, here's an equation. You should solve this equation. And after you've solved the 20 equations like this, you might be very lucky, and we'll tell you why you were solving the equation in the first place. Most students, by the time you get there, have completely disconnected from what the equation was, why they cared, why they were doing it. So that's what I mean. The equation may be very useful, but start with a problem you care about, and maybe the equation can help you cycle faster. Maybe the equation can help you go faster on your bike, and then you might be more interested. If you're interested in cycling faster, you might be more interested in using it to help you. So the organization I founded a few years ago, Computer-Based Math, is basically trying to make this transformation happen. And we've got a slight difficulty in how we talk about this, because you can talk about it as changing maths, or you can talk about this as a new subject called something like computational thinking. And it's a bit difficult to know, do you want to change maths as it is, or do you want to introduce a new subject? Which is the easier way to make the change? But it doesn't matter in a way. What we're trying to do is, the mission is pretty simple. It's simple and it's hard, but it's simple to describe. The mission is build a curriculum assuming computers exist. Seems obvious, but nobody has yet done it in the world for mathematics. Every curriculum around the world assumes that the human is the calculator. And one of the things I've often said is we want first-rate human problem solvers, not third-rate human computers. Now, one of the problems in trying to do this is you need to decide what is it exactly that you're trying to hit. What outcomes are you trying to hit? And we've, in fact, ended up building sort of a list. You can look these up on our website at computerbasedmath.org/outcomes. But these are the things we're trying to get people to get to. Why are they studying the subject, and can we be explicit about it? You know, confidence to tackle new problems, a very important aspect of applying maths. So we want people to be able to apply maths in the real world, and that involves writing and deciding on new outcomes, because most of today's curricula don't have a broad enough set of outcomes to match what we need. We also ended up building a curriculum backwards, so we've ended up building the sort of modules I described in order that we can work out which areas of mathematics we need. You know, we're probably the predominant math company in the world, math organization. We kind of interact with math in more ways than anyone on the planet. We've dealt with math people for something like 30 years in building software, but also hiring them and also using mathematics, etc. So, and even we can't immediately figure out which bits of mathematics are the most important. So we need to actually try real problems to figure that out. Another really exciting thing you can do when you start to think about this is reorder the curriculum. You might ask, why do we teach things in the order that we teach them in? And it's very interesting to look at this. Well, the thing is, at the moment, the curriculum is ordered by how hard it is to calculate that thing in the curriculum. In the future, we can order it by computational complexity, by conceptual complexity, how hard it is to think about the problem. So some examples. Why do we teach two-dimensional geometry before three-dimensional geometry? Well, I don't know which is best, but if you think about it, as a child, you are more used to three-dimensional than two-dimensional, right? Because you're picking objects up. The reason, of course, has been it's very, very hard to compute things in 3 dimensions. It's hard to visualize them, but we have computers to do that and help us with it. There's one paradox to that particular one, which is that, of course, with mice and screens, children are now more used to 2 dimensionals than they used to be before computers. So maybe that's a complicated one, but it's interesting to think about that. Why don't we teach machine learning in primary school? You see, machine learning is very interesting. Machine learning is when you teach the computer, without knowing the algorithm, you teach the computer to learn, like you show it a series of images, and you tell it what each of the images is, and it then learns to recognize those images. That's actually very like how children learn on the surface anyway. It's actually very easy for a child to understand what machine learning, how to use machine learning. They don't understand what's happening on the inside, but nor do I, much of the time. They can use it. So machine learning is something that comes very naturally, very early. There's no reason to leave that late. It's computationally complex, but it's conceptually quite simple in its use. Calculus. Most people in most jurisdictions learn calculus very late, like when they're 16 years old or older, often. Maybe you start a bit earlier. Why? Well, one of the things I like to show is it's actually, this is something I did with my daughter many years ago when she was very young. I said, so I'm going to make more and more sides on this polygon. What happens when you have a really, really, really large number of sides? Right? Well, this is a small introduction to the idea of infinitely small sides, and you can start to work out things about areas and so forth. Again, the concept of making smaller, 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 pushing to the extreme, is a young age thing that we can do much earlier. If you think about physics, why aren't we thinking more about thermodynamics earlier on? The idea that when you change the temperature, things vibrate harder and the pressure goes up. Or when you make the container smaller, that somehow things get more pressured in there. these are ideas that you can see in a simulation rather early. They seem quite natural ideas, and it's good to get people those sorts of experiences. And let's see. For some reason we got a gremlin here, but anyway. So I just wanted to wrap up for a few minutes and so hopefully move to the next slide here and try and explain. There we go. Whoops, we went slightly too far forwards there at once. One of the problems in reforming things is that assessments in most countries are very central to what's taught in schools. And so one has to think about how to deal with the assessments and how to deal with ways to help assessments work. And we have some ideas about how to do that to help those sorts of reforms happen. I suppose my big message, really, if you summarize what I've been saying, is this, that we have a choice now in this area of life. We have huge automation that's come to intelligence, in a sense. In the past, we had eras of industrial change. You know, we had agricultural change. We had the industrial revolutions. Now we've got a revolution in a sense of how we use computation, and this is hugely significant. And we know this, and of course we call this artificial intelligence. The question is what you do with this. You can decide in education that, you know, now we've got the machines, we should just go on pretending to be the machines and doing what the machines now do. Or you can stand on top of it and go further. And in the end, I think history tells us that the human needs to stand higher on the machinery and not pretend to be the machine. Work a level up from the machine, don't compete with it. When it's a successful machine, and computers are very successful. I found this quote from Steve Jobs. Steve Jobs was very influential on our company because, amongst other things, he came out with the name Mathematica for our software, and he was at our release event 30 years ago in 1988 when we first released Mathematica. And one of the things he said shortly after that was, Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar. A very Jobsian kind of quote. Now, why have I highlighted will? I put will in red because he made one mistake in this quote. He should have said should. We're still waiting. Mathematica and other technologies did revolutionize the outside world, but they're yet to revolutionize school education. And so in a sense, that's what I was very pleased to find this quote. It was long after I started working on computer-based maths, but it was interesting to see that Jobs was already thinking about that then. And one of the things I think everybody who is in control of these things should be asking is, are we prepared? Is your country or other countries prepared for, in a sense, the computational knowledge economy, in which we go a step up from knowledge to this modern sort of automated knowledge and the things that humans can do? Many countries, it's still early days. Greece might be able to leapfrog other countries in doing this, even countries that seem like they're very high in PISA, for example. Some of those countries think they have it all figured out, and actually they haven't. They're playing on the wrong playing field. So I think there are real opportunities here, and I hope that's something that can get started sometime in Greece. So join our journey, Fix Education for the AI Age, and yes, I look forward to your questions. Thank you very much indeed.